So we are trying to figure out what in the world this is talking about. We read this little section on differentials, and it told us that the differential is dy. But we have to kind of have some understanding of what that means. So we know, in general, f prime of x could also be written as dy dx. Okay, that's two notations for derivatives. If you just multiply that dx to the other side, then you get that dy is the derivative times dx. Okay, so the variable dy depends on x. Now we have to have some kind of understanding of what dy and dx really means. And so that's where the graph comes into play. So the book has this picture. On the function itself, if you take 2 points on a function, then the amount your x value went up is the change in x. Okay, so from here to here, that's the change in x. Then between those 2 points, the amount the y increased is the change in y. Now it's easy to find if we have those actual points on the graph. To find your change in x, you subtract your x's. To find your change in y, you subtract your y's. We can also talk about the tangent line. Okay, we know how to find the tangent line. It's used a lot of times because it's easier than dealing with the function itself, just like we talked about yesterday. If I just ask you to find the square root of 3.995, you can't do that. But we did the linear approximation to get an equation for a line close to there, and then we could use that line to approximate the y value, correct? So this is saying if you use the y, the amount your x increased, that's your change in x. On the tangent line itself, that's referred to as dx, but that's the same for both. Whether you're on the line or the curve, change in x and dx are the same. The difference is change in y and dy are not the same. Change in y is the amount the y value increased on the actual curve. Dy is the amount the y increased on the tangent line. So a differential dy is estimating how much your y value changed on the tangent line. So not the true curve, but on the tangent line. Okay? Questions right there? Okay, so first I want to do an example to kind of solidify the difference between change in y and dy. So I want to compare these two things. We will find our change in y, we will find dy. Our function is x cubed plus x squared minus 2x plus 1. And we're going to do two different versions. Part A, we're going to change from 2 to 2.05. Change in y is the actual amount the y increased on this function. So what would I need to do to find the change in y? Yeah, we have to plug in our x's. So we first would have to plug in a 2, and then we have to plug in the 2.05. Alright, so if we plug in 2, we get 8 plus 4 minus 4 plus 1, so that's 9. If I plug in a 2.05 for my function, get 9.717625. So, how do you find the change in y? subtract those 2 points. So the actual amount that y changed is positive 0.717625. So the actual amount that the y increased, and I know it's increased because it's positive. Change in y could be a negative, it just means your y value decreased. So we get this answer. Now I need to approximate dy. dy involves doing the derivative. So in general, dy is f prime of x times dx. Alright, we need f prime of x. So what is f prime? So now we need to plug in. X is your beginning value. So what was the starting x value? 2. Dx is the same thing as the change in x. How did my x change to get to my ending point? It went up 0.05, so dx is a positive 0.05. So if we plug that in, we put in a 2, we get 4 times 3, so 12, plus 4 is 16, minus 2 is 14, times 0.05. So my dy is 0.7. So what that tells me is on the actual graph itself, between these points, my y would go up by 0.717625. If I were trying to use the tangent line to approximate it, benefit of the tangent line, calculations are easier, then I would have estimated my y to increase by 0.7. So you can see they're not too far apart. The tangent line is the approximation. That's what a differential is. It's like approximating the change in your y. I want you guys to try to set up B for me. So to actually find a change in y, you have to plug in 2 and 2.01. We already put in 2 and got 9. When you put in 2.01, what'd you get? So change in y, you subtract those and you get 0.140701. So the actual increase in y is that. dy is like approximating that increase. And so we know that's found by doing f prime of x times dx. We already know f prime of x. We did it on part A. You need to look at this when x is equal to 2 and dx is, okay, so I'm still plugging in a 2 for my f prime, so that's still 14. The only difference is now I'm taking that times 0.01, and what does that give me? 0.1. And so we see this was even better, and that will be true in general. The closer you are to your starting point, the more accurate your tangent line approximation will be, because we know, we're looking at the graphs, when you're really close to this point, there's not much difference at all between the actual curve and the tangent line. The further away you get, the further the gap between the tangent line and the curve itself. So the further we get from 2, the worse the approximation would be. Any questions with that one? So let's look at this. The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. This is showing us the other use of this differential. A differential is like talking about error. So when I say the error in the radius, that is talking about dr, the differential in r, the error in my r. So we could be off by at most 5/100 of a centimeter. I want the maximum error in volume. So what variable would I use for the error in the volume? dB, yeah. Okay, so we have to think about this. We are talking about a sphere. Radius of a sphere is volume of a sphere is 4/3 pi r cubed. So now we need our derivative. So our differential, when we do it with differentials, there's different ways to think about it. Probably the easiest way is whenever you take the derivative of a variable, just put d whatever that variable is. So the derivative of v would be dv. Here my 3 comes down, so that's 4 pi r squared, and the derivative of r is dr. Another way to think about it, before we've said this would be like dv dr, the derivative of v in terms of r. And so if you just multiply that dr over to the other side, you get to this point. So now we plug in. We don't know dv. My r is 5. No, it is not. It is 21. I don't know where I got 5. So 4 pi times 21 squared. dr is 0.05. Let's just go ahead and put all of this in our calculator, including the pi. So this is actually a concept that is used in manufacturing. You know, if you are making a part, you have to have it so accurate that it will actually work for its intended purpose, right? Now we know that everything isn't perfect. So if you go out and make 100 parts, will every one of them be exactly the same? No. But we have to have that window of what's acceptable and what's not. So this is saying, okay, let's say when you did this, your radius was off by 5/100. That sounds very, very minimal. If you think 5/100 of a centimeter, that is very, very tiny. But what we're seeing is how far off will that throw my volume? And so what did we get? Like 277.088. So that is the maximum error in volume. We were in centimeters, so this would be cubic centimeters. So that's saying if you allow your radius to be off by 5/100 of a centimeter or less, the biggest error in your volume would be 277 cubic centimeters. Okay, and that's an important concept, being able to look at how will that little bit of change in my radius impact my final product here. Questions there? So we are actually done with this section. I gave you a few problems yesterday, so today I'm going to add okay. On 35, it asks you to find the maximum error and the relative error. We have not talked about relative error. You are just doing the maximum error on this. So you have a lot